No, I haven't clicked it yet. Come around. How's everybody get here? All right, if you have your homework,
I had a test today. He didn't go well. It needs to be over.
It's almost over. Your hours are made.
The calculation.
Because it's a short week. What happened?
I started being appreciate
All the homework
It was like, it was over 100. Survival, probably survival.
All right, so the questions that you guys had for me fell into really 4 big categories. I'm going to do my best to work through all of these categories today. So there was a bunch of questions on the difference between Km, Kcat, the Michaelis-Menten equation. What are the assumptions for the Michaelis-Menten equation? What are the exemptions in the Michaelis-Menten equation? We'll work through those. Everything inhibitors, apparently. Several people wrote inhibitors, so I'm assuming that means, does anyone need the handout that we had on Wednesday? Everybody have that? Okay, good. We'll look at that. Graphs, I had several people that just wrote graphs, question mark. So we will look at graphs in general and then do some problems with them. And then if there's time, I'll go through the serine protease mechanism. If I don't do it today, I'll definitely do it next Friday before the test. But I thought like these first 3 kind of all go together. And the last one's kind of a funky one that kind of is off to the side that we'll definitely get to. So. So the Michaelis-Menten equation, I don't have PowerPoints for this obviously, so we're just going to, you just have plain paper, we're just going to work through some of that. So the Michaelis-Menten equation, when you're thinking about it, these are the things you need to know. So you need to know the actual equation. You need to know the 4 assumptions that let us get to the Michaelis-Menten equation. Then you need to know the 3 exceptions for the Michaelis-Menten equation. So let's do this in order. All right, so what does a V, scripty V with a little 0 stand for in English? Initial velocity, good. And let's take a look at some of these other terms that are in this. All right, so we decide that V0 is initial velocity. What does bracket S stand for? Substrate concentration. Good. What does Vmax in words stand for? Maximum velocity. True. What is it measuring the velocity of? The reaction. So it's measuring the velocity of the substrate, thank you, Mia, combining with the enzyme to make product. So it's measuring that velocity. How fast, really in general, how fast product is being made. So how fast P is made. If I drew one of these hyperbolic curves that looks like this. First of all, what is this curve demonstrating? Let me back up. What do I put on the x-axis for this kind of curve? Substrate concentration. In that case, what would I put on the x or y-axis? Okay. What is the hyperbolic curve asymptotically approaching? Vmax. Okay. So I'm looking back at my equation up here, my Michaelis-Menten equation. There's a few different ways we can define Vmax. Looking at my graph, what is one way I could define Vmax based on my graph? Definitely a homework question about this. Half of Vmax. So if this is Vmax, half of Vmax would be here. Vmax over 2. I would draw across to the line and then down to the x. And where that hits, that is Km. If that is true, what would be the units of Km? Whatever, right, concentration. It'd be whatever the same units for, whatever the units for substrate were, are now your units for Km. So it should be a concentration like molarity, micromole, parts per million, something. Okay, so one definition of Km is that it is Vmax over 2. What if I wanted to define Km in terms of rates? This was on your quiz. So we go back to our original think about it amongst yourselves for a second. Okay, Km is defined as the rate of disappearance of ES. So, what are the two ways that ES could break down? Those go in the pop. So Km is a measure of the disappearance of ES. So if Km is measuring the disappearance of ES, there's two ways it could disappear. It either breaks back down to E plus S, or it goes forward to E plus P. So those would be on my numerator. The denominator is a measure of making ES. So you could think about it as products over reactants. That's a good way to think about it. That there are two ways to make products out of ES over one way to make ES. If that is more logical, that's a good way to think about it too. All right, so those are all true. There's another way that we could define Km, which is in words. What is it telling us about this reaction? It is telling us the efficiency of making the final product. So it's the efficiency of the substrate enzyme reaction. Let me use the exact words I had in my notes. That way I'm self-consistent. Enzyme affinity, that's a better word. So in your homework, there was at least 2 problems that we looked at enzyme affinity. One, there was some enzyme, hexokinase maybe, that could choose either glucose or fructose. And you looked at the Km, and you're like, oh, the one with the, is it higher or lower Km is more efficient, or more lower? So a lower value tells you that's more affinity, which, if you look at the math over here, the bigger the denominator, the smaller the value. So if K1 is much larger, which means it's going this way, then Km is a smaller value, which means it is a good fit. The S and E are a good fit together. So you had at least 2 homework problems where you got to look amongst the Kms and you picked the one with the smaller number, which is the better choice for the enzyme. Okay, any other questions on all the different things that Km tells us? Questions about Km? Okay, then let's look at Kcat and how Kcat is different than Km. Yeah, let me do the Kcat and Km, and then we'll do the assumptions. Yep. So I'll do Kcat, Kcat over Km, and then we'll back up to the assumptions and the exceptions. All right, so Kcat. Is defined as a measure of catalytic efficiency. It is also called the turnover number.
Is this part of what we just did, or is this coming in a whole new section?
I would say it's similar because the only way you get to Kcat is by knowing the Michaelis-Menten equation. And then I'll back up and I'll do all the assumptions and the exceptions. But we'll define all the terms first and then backtrack. So Kcat equals all of those things. It's a measure of catalytic efficiency. It is the turnover number, and mathematically is defined as Vmax over enzyme total concentration. Looking at our same equation we've used a bunch of times before. Which one of those mini Ks tells you about the enzyme substrate making product? K2. K2 is a measure of the turnover number. So 4 for most reactions, Kcat is E2. You can think about in terms of the E plus S making EP has now left you back with E again, which means it can come back and grab another substrate. So you are measuring how fast the enzyme substrate complex breaks off into its 2 separate parts again, so it can come around and grab another substrate. So that's what I mean by turnover number. How fast, if you're thinking like you're going through the drive-through It's how fast that order comes up, you get them the foods, the car drives off, so the next car comes in. For those with fast food experience. Yes?
Can we assume that for the reactions we're using, KCAT is always equal to K2?
Yes. Yeah. The only times it would not be is when we talk about exceptions. And so I will specifically tell you, this is an exception case, and then something. So we have to figure out how fast we can get our enzyme substrate into our two product enzyme combination and come back correct. So for most reactions, KK equals K2, which is true when our enzyme total is about our enzyme substrate concentration, and V0 is approximately Vmax. At what concentration, low or high, substrate is this true? High. The only way this is true is if you're at high substrate concentration. What is the first assumption you have to make? Substrate concentration's high. What do we call that? It has two letters, start with two S's, steady state. Which is assumption number 1. So now I'm going to move into the assumptions. Right, so this is our first assumption. Number 1 assumption for Michaelis-Menten equations to be true. If this is not true, your whole argument falls apart. Let's say, I guess I'll, yeah, I guess I'll do the graph now. So this is one of the other important graphs that we're going to look at. So on the y-axis I have concentration, on the x-axis I have time, and I'm graphing this equation, making this assumption. So at the start of my reaction, I should have high substrate concentration. As time goes on, my substrate concentration should decrease, right? At the start of my reaction, how much product do I have? A lot or 0? 0. At time, thousands of hours, do I have lots of product or little product? I should have lots of product. So those should cross each other as one's decreasing, the other one's increasing. So that should make sense. Let's now include our enzymes. At the start of the reaction, comparatively, is there an equal amount of enzyme or not very much enzyme? There shouldn't be very much, right? The substrate should definitely be the majority product in there. So I'll put my enzyme concentration here. As time goes on, what happens to my free enzyme concentration? Increases or decreases? It has to decrease. In fact, it decreases and then flattens out. And then goes up again. So that's my free enzyme. Enzyme with nothing bound to it. Decreases, flattens out. At the very end, it goes up again because there's no substrate to do any reactions with. So now the fourth part that we haven't looked at yet, right, is this guy. So if you're color coding, let's see, this was red, this was blue, this was black. What color is that? Green. So then the last thing we haven't looked at is the enzyme substrate combination. So how much of enzyme substrate complex should there be at the very beginning of my reaction? None. There should be none, right? So it's also going to be down here at 0.0. As my reaction progresses, it should increase and then level off. What happens as my reaction progresses to the very end? It should decrease the same amount as my free enzyme increases. So what do I call the zone right here where my concentrations of enzyme substrate complex are? That is the steady state assumption graphically. Like, we are in the flat zone. Questions on this figure? Does that make sense now? We'll walk through a little slower. Yes? Okay. Let's see, that's assumption 1. We did that. Okay, so this graph also tells us assumption number 2. Assumption number 2 says that enzyme total that the total enzyme is in only one of 2 options. It's either free or it's bound up with one substrate. There's only 2 kinds of enzymes. One is doing chemistry and one is waiting for a substrate. And together, they add up to the total enzyme concentration. Questions on that assumption? That one should be pretty straightforward, right? I mean, total enzyme, you're either bound up or you're doing chemistry. Which you can see from the graph that as one increased, the other decreased, and that the overall enzyme amount was even all the way through. They were just in one form or the other. Okay, let's do the other 2 assumptions. So we will only measure the rates at the beginning of the reaction. So we only measure the rates in this very first part of the reaction, where substrate is still high compared to enzyme concentration, but we are not in the super high concentration where everything is pretty much Vmax. We measure in this part. if we measure the initial velocity, we can then write our Michaelis-Menten equation in terms of initial velocity. And I recognize the initial velocity is not a great term, because if you're taking a physics course, apparently initial velocity means 0. Not true in this case. Biochemistry assumes that initial velocity is not 0, that there is velocity at the start of a reaction. Apparently, we didn't get together on our terms. Physics, chemistry, biochem. Got a little confusion there. So initial velocity is not 0. It has to be a value. Yeah, I mean, the initial velocity is 0, but that sounds redundant. So. So the fourth and final assumption that we can say
Actually, like the velocity initial, that's to let you write the things.
yes. Our final assumption is that the maximum velocity is only related to K2, because we assume that, I guess, as part of this. Because we assume, bless you. We assume there is no K2 minus. There's no reverse of K2, right? So there's K1, K minus 1 in opposite directions. In theory, there'd be K2 and K minus 2. We assume that there is no K minus 2, which means the maximum velocity is only related to the forward direction and the total enzyme concentration. All right, any questions on any of that? 4 assumptions. Okay, so let's zip through our 3 exceptions and then do some graphing. Okay, first exception is that there's more than one substrate. If there is more than one substrate, it doesn't follow our assumption of our straightforward reaction. This is no longer true. So our assumption that it's E plus S makes 1 complex only goes forward to E plus P. That is no longer a true statement. Which means steady state may or may not be true depending, because you have to have both substrates in excess of the enzyme. So both substrates have to be in excess. So again, an exception doesn't mean the Michaelis-Menten equation is no longer usable. Just means you have to make some adaptations to make it still usable. So you'd have to make sure that both substrates are now in excess. To continue on. In a multi-step equation, Or it'd be like, where now there's 2 intermediate steps, maybe more intermediate steps, right? So A and E combine together to make one temporary product, but you have to have a second thing come in to make the actual product you want. Some sort of multi-step reaction in that way, where it's not just one substrate, one enzyme. It's multiple substrates with multiple intermediate phases. We can no longer simply say that kcat is a measure of K2 because there's multiple equilibrium steps and there's no one single straight arrow. And so if that's not true, then this can't be true either. Vmax is no longer related to K2 times the enzyme total concentration. Again, not irrevocably broken. You can figure those things out. It's just not as straightforward. So our assumption was it looks like this, with one substrate, one enzyme. A non-hyperbolic reaction, it looks something more like that. So like in the case of hemoglobin, you have to add oxygen and then it kind of levels off until the whole hemoglobin molecule shifts and then it increases again. Then you have to add another oxygen, it would increase again. And so non-hyperbolic typically means that there is more than one active site. So you can't assume steady state because steady state's really just a measure of this right here. That at some point the velocity levels off. So you can't make that assumption.
The one on the right is the canonical.
Yep. All right, questions on our 3 exceptions? No? Okay. In that case, let me do some graphs, because there's some questions about graphs. And then I'll do inhibitors if there's time. All right, so this is one of your homework problems. This could be a possible test question, right? I would give you a graph, and just like in the homework, given the graph and the equation of the line, what is the first thing you have to do in order to find anything on this graph? I would write down the Lineweaver-Burke equation for this kind of problem. So 1 over V0, make sure I get it in the right order so I don't mess everybody up. Should be Vmax over Km. I'm on the wrong page. No, the other way. So besides knowing the Michaelis-Menten equation, also know the Lineweaver-Burke, which if you know one, you really know the other, because it's just the inverse of each other. Right? I mean, they're just 1 over each other. It's not that big of a deal. All right. So if that's my Lineweaver-Burke equation for an enzyme, So now I would like you to label the graph with the parts of the equation. So what I mean by that is, which one of these variables is the x-axis? 1 over s, which you should be able to get based on the fact that it's giving you inverse molarity, or it's saying it's 1 over some enzyme, substrate, something, something. That should be a gimme. What do I put on the y-axis? 1 over v0. What does the slope equal? Okay, more v max. And what is the x, or let me do what does the y-intercept equal? Okay. And then the other one you'd have to know without using the equation is what does the x-intercept equal? And the third part will be just like in your homework. Find Vmax, find Km, using the equation of the line. Which way down? This way? Okay. So I want you to calculate Vmax and Km given an equation of the line. Fair enough. How would I figure out what Vmax is? It's the inverse y-intercept. So what would I set x to find the y-intercept? Okay. So Vmax is just the inverse y-intercept. If I wanted to find Km, there's 2 different ways you can do it. One would be the slope if you found Vmax first. What's the other way I could do it? I think these are the easiest ways because they're independent of each other. So if you mess up Vmax, you don't necessarily mess up Km. But either way is fine. Questions on that? Okay, I could ask you, one would be draw a competitive inhibitor graph. So, just like you had in the homework, first thing you have to know is how to draw a regular, right? The only way I can compare it is you have to be able to draw a regular, non-inhibited line, because otherwise it doesn't make any sense. So what I'm really asking is 2 parts. Draw the non-inhibited line, draw the inhibited line, and then make sure that you label your axes. We can do this in any order. Let's do the axes first. What would I put on the x-axis since we just did this? What would I put on the y-axis? Okay, so let's say this is my non-inhibited. If it is a competitive inhibitor, one thing stays the same and one thing changes. The slope changes. So if the slope changes, what happens to the y-intercept? Stays the same. So if the y-intercept stays the same, but the slope increases, it would have to look like that. So what does that tell you about Vmax for a competitive inhibitor? Km changes. Vmax is constant. That's all right. Vmax is constant because all I did is I pivoted, right? I was here, I pivoted, so the slope changed, but the Vmax point did not change. What must this tell me about what Km? Change, not change? Change. All right, so Km changed because it was here, now it's here. And if you haven't worked through your little worksheet yet, this would be a good time to make sure you finished it. In fact, Km decreases. The slope increases, but Km decreases. Because Km, the overall value of the slope increased, which, let's see, what's the easiest way to think about this? I think the easiest way to think about it is in terms of the equation. Oh, unless Megan's going to solve it. Megan's going to solve it back there. I'll do it in terms of this. So here's my equation, right? E plus S, K1K this way. No, the one we were confused on was the uncompetitive. This one we were all straight on. Apparently till now. All right. So if you think about, it can either go this way or it can go this way. Km is decreasing because the amount of enzyme available to go this way is decreasing because of the inhibitor. And so if Km is a measure of the enzyme substrate productively making product, if there's no ES, obviously this whole value has to go down. You can use the same argument when you're talking about uncompetitive inhibitors. Km also has to decrease because there is less of the enzyme substrate complex productively making E plus P. It's being pulled off to make ESI, which is no good. That's no reaction. So if the value of this decreases, then the whole thing decreases. You could look at mixed inhibitors. Km could decrease because ES is decreasing, or it doesn't make ES at all because it goes down this way. So in this case, the Km could increase or decrease because the free enzyme concentration is actually disappearing because some of it's going this way and some of it's going that way. So Km variable in this case. That's right, Courtney, yeah.
How is competitive
And
if one of them Km is moving to the y-axis, the other one is moving to the y-axis?
for the competitive or the uncompetitive?
For the competitive Km is moving closer to the y-axis, right?
Yeah, but it's -1 over, so the numerator, no, the denominator is getting smaller to make the number a smaller negative, which makes it close to 0.
But then uncompetitive, as you add the away. So they have to be the opposite.
Yeah, let me look. Let me see if I can come up with a better way to explain it. Since we only have like 5 minutes left, what I'm going to do is you now have a take-home quiz. It's not an easy quiz, which is why you can't do it in 5 minutes. So what we're going to do is we're going to do a take-home quiz. It's going to take longer than 5 minutes, for sure. And on Monday, we will answer these last 2 questions, wherever my 2 questions are. We'll finish going through this. Right, we'll work through the worksheet and answer all questions about inhibitors. And then we'll do the serine protease mechanism Monday. Yeah.
So are we still working on the pretest?
Nope. It is an individual take-home quiz, closed notes. I'll be able to tell if you've been cheating. If it's going to be take-home, it has to be an individual quiz. And it has to be closed notes. I don't think you'll all fail it. If you did the homework, then you're fine. It's pretty much the homework questions on a quiz. So, 2 multiple choice, write out the equation, do a plot.